So we've seen an example of a system of two equations where elimination works really efficiently. All we had to do in this example was add these two equations together directly, and immediately the y's went away. And once the y's went away, we could find x, back substitute, and then use the x value to find the y value. So elimination was like falling off a log in this example. Didn't have to do anything but just add the equations together and we were off to the races. Let's try and apply that same approach to the last problem that we looked at from last Monday. So suppose that we try that approach on this system, system number 2 down here. I might look at this and say, all right, if I'm going to copy what I did before, I'm just going to add these two equations together, and that should eliminate one of my variables. Well, on the right-hand side, I get 11 plus 0. It's going to be 11. On the left-hand side, I get negative 3x minus 4y minus 5x minus 3y. And then I'll go through and I'll combine all of my like terms. How many x's do I end up with? Negative 3 minus 5. I end up with negative 8 x's. And on the y side, negative 4 minus 3, I end up with negative 7y. And what we notice is what didn't happen this time. Yeah, we didn't succeed in canceling out one of our variables. We didn't eliminate y or x. Right? The equation that we got still has both variables in it. And so clearly that's not going to help, because I can't then solve this equation to find the specific value of x or a specific value of y, because both variables are still entangled in that equation. So the one step of elimination that we haven't thought about yet is what happens when the equations as we're given them are not sufficient by themselves to cancel out one of the variables. And so the first step in the elimination process that we didn't have to contend with last time, but we will have to contend with this time, is a step that comes before the addition. It's a step where we ask ourselves, how can we modify one or both of these equations? How can we modify these equations so that elimination will happen when we add them together? So we have a little bit of setup to do. Because in the first example we looked at of elimination, there was a plus y in the first equation and a minus y in the second equation, and those cancel each other right on the nose. But if I want to get rid of the y's here, I can't do it with the equations as they are. In particular, one thing we notice is that both of the y's in this example have negative coefficients, negative 4 and negative 3. So if I add those together, I'm definitely going to get another negative number as the coefficient of y, when what I want to get is 0. So what do you think? What could I do to, let's say, this first equation, negative 3x minus 4y equals 11. What could I do to that to get us at least a little bit closer to something which will be able to cancel out with the minus 3y if we were to add them together? So what are some ideas? The idea is, let's multiply this equation, which means multiply it on both sides by the same quantity, right? Let's multiply this equation by something which is going to turn the negative coefficient on the y into a positive coefficient instead. So what's something I could multiply by to do that? So if I multiply by 3, so let's try it. That's going to give me the equation negative 9x minus 12y equals 33. And then in my second equation, I'm going to have minus 5x minus 3y equals 0. And if there's any doubt as to whether we're ready for the rest of our elimination process, let's just try adding these equations together and seeing what we get. On the right-hand side, I'm going to get 33. On the left-hand side, I'm going to have negative 14x minus 15y. So, all right, we still quite haven't gotten there, right? Our y's are still hanging around, our x's are still hanging around. But multiplying by 3 is probably a good idea. It gets us a little bit closer. What else might we want to do? If multiplying by 3 by itself wasn't enough, what's something else we can try? The observation that we want here is that the process that we're about to undertake is very similar to the process that we undertake when we're looking for a common denominator between two fractions. Right? We're trying to find a number which we can scale -4 and -3 up to, which is equal, which is a common multiple of -4 and -3. And one of the ways of finding a common multiple of two numbers is by multiplying them together. So let's take that approach for a second. If I multiply -4 times -3, actually we could even forget about the negatives. If I just multiply 4 and 3 together, I'm going to get a common multiple 12. If we were thinking about this like a fraction problem, 12 would be playing the role of our common denominator. And then our task would be to take each of these two equations and multiply it by something, possibly a different something, for the first equation as for the second. But multiply each one by something which is going to scale up the coefficient of y into a 12. So we've already seen that multiplying the first equation by 3 accomplishes that. Right? Multiply the first equation by 3, I get -9x minus 12y equals 33. What would I need to multiply the second equation by in order to turn the coefficient of y into 12? I would multiply it by 4, or -4. Let's worry about the signs next. If I multiply that by 4, I get -20x minus 12y equals 0 times 4. That's 0. So notice that that same strategy that we use when we're finding common denominators for fractions and then balancing out their numerators, that's the same arithmetic that we just did here. Right? We wanted the coefficients of y to be 12 in both equations, so we multiplied the first equation by 3 and the second equation by 4. And now I have -12 out in front of both of my y's. And so we're almost there. The reason we're not all the way there is if I were to add these two equations together now, what's -12 plus -12 going to be? It's going to be -24. And so I don't quite get rid of my y's by adding these two equations together. So I just want to make one more change. What's one more change that I can make before adding these equations together that will make it so that my y's cancel? Negative. Where do I want to put a negative here? Yeah. So really, what I want is not to have a -12 and a -12. What I want is to have a +12 and a -12. So that when I add them together, the equal and opposite addition cancels out to 0. So I can do that by, instead of multiplying this equation by 3, multiply it by -3 instead. Or equivalently, just put a minus sign out in front of both sides. Right? Now, distributing the minus sign, minus -9x is going to give me positive 9x. Minus -12y is going to give me plus 12y. And then I'll have a -33 on the right-hand side. And now, finally, we're set up for an addition which will succeed in canceling the 12y's from my two equations. The right-hand side of my sum is going to be -33. Left-hand side is going to be 9 minus 20, that's -11x. And then my y's plus 0y are going to go away. And now we've succeeded in eliminating the y's. Dividing both sides by -11, I then find out that x should be equal to 3, which is the same solution we found when we did this by the method of substitution. Then we would just have to substitute this x equals 3 back into any of our original equations. By the way, you're also free to use the non-original equations if you like, but generally the original equations are a little simpler, so I'm just going to use that. And then we'll find our value for y the way we usually do. -15 minus 3y is equal to 0, and so y ends up being -5. So the first step in the elimination process is not generally to add the two equations together. The first step is to ask yourself, what will it take to balance the coefficients of one of my variables? In this example, we singled out the y. What will it take to make it so that the coefficients of y are equal and opposite? And an easy way to do that is to find a common multiple, just like a common denominator, for the coefficients, and then use that as your target. We set 12 as our target for the y coefficients here. And then we did what we had to, multiplied the first equation by -3, the second equation by +4, so that what we got were equations in which the y's had an equal and opposite coefficient of +12 minus 12, which made it so that when I added them together, the y's then canceled. And I can solve for x, back substitute, and find my y. And that's how elimination works. This is probably an example of the most work that you would have to do in an elimination problem. Some elimination problems are already set up for just adding immediately. Most are not. And so this process of balancing is typical of what you'll have to do in most problems where you use the elimination method.